Let's look at the graph of y equals x cubed. We see a place where there's a change of concavity from concave down to concave up, and in fact there's an inflection point right at x equals 0. The graph of y equals x to the fourth has a local minimum, and it has no inflection point. There's no change of concavity. Now let's notice something about the first and second derivatives in each of these cases. The second derivative is 0 at x equals 0 for this graph. Now let's look at this function. We notice that here too, the second derivative is equal to 0 at x equals 0. So both of these functions have the property that the second derivative is 0, but only one of them is a graph that has an inflection point. What is going on here? Well, we can see the difference between the two when we look at the sign of the second derivative close to this point. So in this particular case, we see that the second derivative changes sign near x equals 0. If we look at the second derivative, when x is negative, the second derivative has a negative sign. When x is positive, the second derivative is positive. So indeed, it does change sign near this point. This is then the signal that we have an inflection point. On the other hand, let's look at this one. The second derivative is 12x squared. This is always positive near x equals 0. There's no sign change, and therefore, there is also no inflection point. This example illustrates the fact that we have to take great care. If we find a function whose second derivative is 0, we must not jump to the conclusion that there's an inflection point there. We must check whether or not the sign of the second derivative actually changes near that point.